Yes, class. Good evening. Am I audible to all of you?
Good evening, ma'am.
Okay. So in the last class, we had started with nuclear and two topics we were able to cover. One was nuclear size and second one was nuclear density. So see class, nuclear size was what? Nuclear size basically, the principle is that volume of the nucleus is directly proportional to radius. So is directly proportional to the mass number. So R is directly proportional to A, R cube basically. How will we get R cube? Because the formula of volume is 4 by 3 pi R cube. So 4 by 3 pi R cube is directly proportional to A. So from here you can conclude that R cube is directly proportional to A. And R is directly proportional to A by 3, where R is equal to R naught A to the power 1 by 3. Then the value of the constant that we use is 1.2 Fermi meter, which is 1.2 into 10 to the power minus 15 meters. Fermi is the unit, the way we use angstrom, the way we use nanometers, like these units. Same way we have Fermi also. In class 11th, you must have done it. Sarah, I wanted to ask, Sarah, the timings that I had shared, I think you were only asking, no? Or was it someone else? Yes, Sarah, because you were, no? So I think there was just a misunderstanding between the batches. It was for other batch. I hope you're understanding. Fine, because I had it off with them. That's why because one more Sarah is there in that batch also. Okay. Then. So your timings are this only. It's just that half an hour before the other batch had to start. That's what you were discussing. Right. Then second thing that we noticed was nuclear. This was nuclear size. Then second is nuclear density. Now nuclear density is fixed for all elements. Nuclear density is fixed. I am repeating. Please understand this statement. Be it copper, be it aluminium, be it germanium, be it silicon, any element if you take from the periodic table, nuclear density is fixed. Nucleus, not talking about the entire element. Nuclear density will remain fixed. So if you see over here for the nuclear density, just do 2.3 into 10 to the power 17. Yes. When you substitute everything, all the formulas in here, you will get the value 2.3 into 10 to the power 17 kg per meter cube. So some questions do come from this part also. In the assignment also I have shared nuclear density and nuclear. I think assignment is now already active. The WhatsApp group, the message came. Let me just check. Nuclear size and density. Yes, assignment 2, nuclear size and density. So assignment is already active. So just look up the assignment. Few questions are there. Let us also practice some questions. See, this says that calculate radius of germanium whose atomic mass number is given as 70 and R naught's value specified as 1.1 Fermi meter. Now, in this case, 1.1 Fermi meters is specified to you, so do not use the other value 1.2 Fermi meter. Fine, 1.1 Fermi meter is specified, so use 1.1. So R is equal to R naught A to the power 1 by 3. Here A mass number is given as 70. A is given already as 70. It can be given through the chemical representation. Chemical representation also we had seen. So R is equal to R naught is 1.1. Let us keep Fermi meter because we can put the final answer in Fermi meters only. A to the power 1 by 3, that is 70 to the power 1 by 3. So 70 to the power 1 by 3. This will be 8 point something. How much? No, 4 cube is 64 round. No, so this will be 4.12. So your answer should be 4.53. Just check the solution. Just check the calculation. It should be around this only. So this much Fermi meters will be your answer. So just take the cube root of 70, whatever is the mass number given to you. Note this question. One more question I am And those who will note it down, you can try this second question. First note this, then we'll do the other one. See, for this question, express 16 milligram mass equivalent energy. See, you know the formula, no? In dual nature of matter and radiation, we did the formula E is equal to mc square, Einstein's theory of relativity. So from that equation only, certain questions will be there from nuclei as well. It's just that formula remains the same. So either if you attempt it from dual nature or here, the formula is same in both of the cases. So E is equal to mc square. Questions actually when radioactivity was included in this part, no? So questions were there directly from E is equal to mc square and then other things got related. Right now you only have binding energy after this left. So that will make your work easier. Again, mass is 16 milligram. So that is 16 into 10 to the power minus 3 grams. And speed of light is 3 into 10 to the power 8 meter per second. So energy will be 16. This will be kg. 16 into 3 into 10 to the power 8 whole square. This much of joules of energy you will get. If you wish to calculate it in terms of electron volt, divided by 1.6 into 10 to the power minus 19. Note down these two questions, then two more questions, let's see. See, this question says that assuming protons and neutrons have equal masses, calculate how many times nuclear matter is denser than water. So basically, you have to compare the densities of water and density of a nucleus of an atom. So see, density of the nucleus, which we have calculated 2.3 into 10 to the power 17 kg per meter cube. And what is the density of water class in SI unit? Density of water. Density of water, you people do not remember. Atif,
1000 kilogram per meter.
1000 kg per meter cube. Others do not know this value. This value you all should remember. In your exam, questions like this only will come, where density of water will be assumed by you. So density of water in CGS unit is 1 gram per ml, and in SI unit, this is 1000 kg per meter cube. Please remember this value from now onwards, because this value will not be given to you in the exam. Some values you have to remember, like the value of H Planck's constant, epsilon naught, permeability. These values you have to remember. So here we have to compare the densities. No? So let's take the ratio. 2.3 into 10 to the power 17 by 10 to the power 3. So this becomes 2.3 into 10 to the power 14. Okay, to this much. The units will get cancelled. So density of a nucleus is this much amount times 2.3 into 10 to the power 14 times denser than the density of water. Fine. Now the last question says that the nuclear, this you all should answer me in the chat box. Note it down, answer the last question, fourth question. After this, I'll do binding energy curve. A mass defect first, I'll do. Mass defect and binding energy effect. Nuclear mass of iron is 55.85. Calculate its nuclear density. Yes. Note the third question. Question number 3. Question number 4. Answer me in the chat box, all of you. At least you should try question 4, the easiest question of all. Yes, so only Krishna has answered till now. Anybody else for the fourth question? Atif, Fatima, Akifa, answers for the fourth part at least. Nuclear mass of iron is 55.85 AMU. Calculate its nuclear density. Hanifa, correct answer. Good, Hanifa. Hanifa and Krishna have answered it. C class. In fourth question, you don't even need to perform any calculation. What did I say? Be it any element, nuclear density is independent of mass number. This was the conclusion and result that you had written. So nuclear density will still be 2.3 into 10 to the power 17 only. Precisely also, if you do by calculations, you will get the answer. You will get this answer. No, this as 2.9 only. So it's fine if you write it as 2.3 into 10 to the power 17 kg per meter cube. Because nuclear density is independent of mass number. So these questions will come in one marker only. It looks lengthy that you have to perform calculations, but the calculations are not involved in here. Note it down, then we'll do mass defect. See, regarding mass defect, what is meant by mass defect? So, mass defect's final formula only I'll tell you. Firstly, just have the number of protons. So, total mass of protons will be, I'll tell you the formula at the end, just go by this line by line because the complete formula becomes very difficult to learn if you do not understand it in bits by bits. So, total mass of proton. Total mass of protons will be how much? So, if you know mass of single proton and you know number of protons, then you can get the total mass, right? If you know mass of one proton, that is MP, let's say this is MP. And how many protons are there? In the last class I had told, does anyone remember? Number of protons, number of electrons was equal to something. I made you write it in the introduction part of this lesson. Z, atomic number. Atomic number Z, electrons and protons are equal to that. So, so if Z number of protons are present and mass of a single proton is MP, so total mass of proton will be ZMP, right? If I want to find out total mass of neutrons, so neutrons I had told you that it is difference between the mass number and atomic number, A minus Z. So A minus Z is number of neutrons and multiply it with the mass of a single neutron. Clear till here? Total mass of protons, total mass of neutrons. And let's say total mass of atom, total mass of nucleus, you can say. Total mass of the nucleus that is present or the atom, let's say that is N, capital N for the nucleus. Now see what is meant by mass. Mass defect is, firstly, it's the difference between sum of these protons and neutrons and nucleus. Difference between these and these means this term minus this term. So what is this term? Total mass of protons is Z plus total mass of neutrons plus A minus Z Mn minus mass of the nucleus. This is known as delta M, which we write it as mass, which we call it as the mass. Now, binding energy. So binding energy is basically the energy that is required to break the nucleus into its constituent items. To break the binding force. That's why we call it as binding energy, though it can be confusing that it is required to bind it. No. It is required to break the binding force. if a nucleus is present, binding energy basically breaks into its respective protons and neutrons. Fine, that is what is meant by binding energy. So binding energy is directly related to the formula E is equal to mc square. E is equal to mc square was there, no? Just make that m as delta m. That is mass defect into speed of light, mc square, like this. That is the complete binding energy, delta m c square. All right. So when you have to calculate binding energy, put the formula of delta m, that is zmp plus a minus zmn minus mn into c square. So you can put complete value of c square, that is 3 into 10 to the power 8 meter per second whole square, like this. By chance, if you are asked to calculate binding energy per nucleon, if you are asked binding energy per nucleon, then take the entire term, take binding energy divided by the mass term. This entire term, binding energy, Zmp plus A minus Zmn minus Mn into C square. Into C square divided by A. This will give you binding energy per nucleon. Now see, class, you will have all the values. You can put it in the formula, final formula, and you'll get the values. But sometimes or what, many a times you are asked to solve all these in terms, you are asked to solve all these and find the values of all these in terms of mega electron volts. And usually by yourself only, from your side also, try to answer in terms of mega electron. So binding energies formula, whatever you get, delta M, multiply it by 931 to get your answer in mega electron. Same thing for binding energy per nucleon also, anything. This is one thing. If you have to get your answer in joules, if it is mentioned in the question, if you are required, you know that right now you have to use it in joules. So then nothing else, you have to put all the values multiplied by C square, that is 3 into 10 to the power 8 whole square. Otherwise multiplied by 930. Let's see, we'll see one more question also. Note down this formula part. Any doubts you have, let me know from mass effect. It's a small topic. One question we'll do from this and one binding curve we have to just discuss. Then we'll finish with this lesson. See in this question, how do we solve? Mass of neutron and proton, you have to remember by your own only. Otherwise, in this question, it was mentioned, and many questions won't be mentioned. That's why when we were doing atomic mass part, I was telling you that remember this value by yourself only. And mass of calcium atom is given. Fine. Okay. Now, see class, one thing. Here we have to use ZMP, same formula we have to use. But let us just find out first ZMP. That is, ZMP part will be the atomic mass. This is given to you. How much is it given? 1.00, no, 1.00787. And Z for the proton. This is given to you already as 40. Right, sorry, 20 here. Z is 20. So 1.007825. So when you solve this, this will come around 20.1733 AMU. Same way, A minus ZMN. So A minus ZMN, A minus Z, that is 40 minus 20 will again be 20. 20 into 1.008665. That will be equal to 40. No, this will be again equal to 20 point something. No. See, this ZMP will be equal to 20.1565. And class, here you cannot round it off. Just remember one thing, class, do not round it off in such questions. You will get these kinds of questions. Last year, binding energy was related. So there's a lot of chance that it can be asked to you in this paper. But if it is asked to you, do not round it off. See, I am not also able to round. Otherwise you'll get your answer as 1100 everything. Because you are talking about nuclei, no? Nucleus is a very small thing. So this will be 20.1733 AMU. Now, what do we have first? We have ZMP plus A minus Z. So this becomes, that is total, you can say mass, total mass of the nucleons. If you add these, you will get 40.3298 AMU. And mass of calcium is given to you 39.962589. Use the exact number that is given. And then at the last we subtract it. Remember, minus M nucleus we subtract it. So mass of calcium nucleus we subtract. So that is 39.962589 AMU. When you will subtract it, you will get the mass defect as 0.367211 AMU. So this is delta M. We have to calculate binding energy per nucleon. So first calculate binding energy. Binding energy will be delta MC square or 0.367211 into 931 mega electron volt. So once you solve this, you will get your answer as 341.87 mega electron volt. We have to find out binding energy per nucleon. So I have told you, for binding energy per nucleon, divide it by mass number. So for divide binding energy by mass number. So this is 341.87 divided by mass number is 40. You will get your final answer as 8.547 mega electron volt. This will be the answer. Here, this question is clear to you. This is a very typical question that comes from binding energy per nucleon part. If you have understood this question, you'll be able to manage other questions as well. Clear or not?
Yes, ma'am.
Others? What about others? Akrifa, you're not responding today. Understood or not? Josefa, Kulsum, what about you? Both the Sarah, Zen. Understood? If you have understood this question, then it will become easy for you to tackle all the rest of the questions. Note it down. Any difficulty you have, let me know and clarify it. Okay, class. If you all have written, if anyone is writing, just stop me. Binding energy curve. See this curve properly, as well as the curves theory part. Everything is written in the handwritten notes now that I have shared with you on WhatsApp. That you can see. And anybody who is not yet added on the group, anyone who cannot access it from WhatsApp, please let me know. I'll share it with you personally or I'll mail it to you, because those notes are very important. And as I'm saying, in modern physics, the theory part is asked a lot. And from the theory part, I have not made you write so much in here. Like other lessons, no, we write every definition, everything. Here we are not writing those things. So for the modern physics part, please refer to the notes. And yes, you will find extra topics also, like radioactivity. Certain topics are extra. So the topics that we have not discussed in the notes, do not just look at it. All right, then, like you can have a look at the Rutherford's model, all these things that I've mentioned. Whichever topic that we have discussed, do that. Otherwise, do not look, because that is based on the earlier old syllabus, not even last year, last year, the earlier syllabus that we used to have before COVID. Okay, so now see, this is binding energy curve. Binding energy curve is basically the graph plotted between the binding energy. You can look on this axis, you have on the y-axis, you have binding energy per nucleon. This is actually binding energy per nucleon in mega electron volt. And on this axis, you have mass number, 50, 100, like this, you have the mass number. Now, see class, here the x-axis is missing, it's just x-axis is also there. Now, what is happening? You will notice that for some nuclei like helium, carbon, oxygen, if you forget these, helium, carbon, oxygen, otherwise, binding energy curve is a smooth curve. Just do not look at this. Otherwise, it's a smooth curve. Like this, you have the curve, right? For some elements, there's a dip that you observe. Like helium, here you have lithium, nitrogen. One more dip is there before oxygen, that is for boron. It has not been drawn over here. So binding energy per nucleon is small for light nuclei, like all the isotopes of hydrogen. Here you have all the isotopes of hydrogen. So binding energy per nucleon is small for light nuclei. All right, it is small, value is small. And in mass number, that ranges from 2 to 20, like helium, carbon, oxygen, they indicate a higher stability. Fine, they indicate a higher stability of the nuclei. Like lithium, boron, all these you can notice. Here, there's a dip that you observed. See, class, understand one thing. Low stability occurs for minima. And when you have maxima, high stability occurs. If the curve has maxima like this, pointing upwards, that means highly stable, higher stability. And if it is minima like these, downward dips, it means lesser of stability. Fine. And for element at exactly at 50, not 50, it is 56. I have drawn it on the screen around 50, but when you plot it, it will be between 50 to 100. That is, for iron, it is 56. So it should be around 56. You'll notice that the value of energy is 8.8 mega electron volt per nucleon for iron. Fine. So the curve has just a broad maxima. And then afterwards, what happened? Initially smooth, then maxima, minima till sulfur. Then iron, you get a peak value, maximum value, and then the graph gradually decreases and drops to around 7.6 mega electron volt per nucleon for other elements like uranium and like this, elements like this. So you have all these elements present with you, iron and all. So when you look at the graph, when you plot the graph also, binding energy curve can directly come to you as well as the conclusion. Yes, many conclusions from this included nuclear fission, nuclear fusion, but those phenomena are not a part of your syllabus, so no need to focus on that. Just remember, you have to plot this graph. Hydrogen, helium, initially the graph is smooth. Then you have maxima, minima dips. You observe these zigzag patterns. The peak ones, maxima, shows higher stability. The lower ones, minima ones, show lesser stability. then you reach a maximum peak value in the graph that has the highest value of the binding energy per nucleon associated along the y-axis, that is 8.8 mega electron volt. Then it decreases as the mass number increases. This is what is binding energy curve in simple terms. I've repeated it also. So those who have not understood, I hope now you have understood. If anyone has any doubt, you want me to repeat it once more, let me know. If you want me to repeat it once more, let me know. I'll repeat it. Otherwise, if we are clear here till here, we can start with semiconductors, the last lesson of your class 12. Clear to all of you? Just write in the chat box, clear or not, understood or not, yes, no. Then we'll move to semiconductors. Only Fatima has responded. Others, what about you?
Yes, ma'am, clear.
Clear? Then I think we can start with okay, then let's start with semiconductors. So this finishes off nuclear. Now nuclear part does not have any other portion included. Okay, let's start with semiconductors. So special purpose diodes have also been deleted from your syllabus, from semiconductors. Special purpose diodes we used to have. See, firstly, Zener diode got deleted last year only. And this year we do not have LED, photodiodes, solar cells, all these topics have also been deleted. So it's again a short lesson only. This is also a short chapter. Firstly, you have classification of solids. So there are various bases on which solids are classified. Directly, we'll not start with semiconductors. Let us just see what are semiconductors. Why are we not studying on how are they different from conductors? How are they different from insulators? We could have directly started with semiconductors. But let us first know what is a semiconductor, how it stands in between insulator and conductor, what are the properties that are similar to insulators or different from conductors like these. So there are various bases on which a solid can be classified. Many things you have also studied in your solid state classification of solids and all. So here, firstly, we'll classify on the basis of resistivity and conductivity. So conductors have low resistivity. Low resistivity. That is rho C. This is very less. And insulators have high resistivity. Resistivity, resistance, conductivity, conductance we have studied in current electricity. Fine. So this is high resistivity for insulators. Coming to conductivity, with reference to conductivity, you have high conductivity. I hope you remember conductivity and resistivity were inversely proportional to each other. So if it has low resistivity, here it will have high resistivity. High resistivity for this is high conductivity. And insulators, whereas, have values of low conductivity. So value of resistivity for inductors, you have the highest, whereas you have it lowest for the conductors. So semiconductors lie exactly in between the resistivity values of conductors and insulators. Same thing, conductors have high value of conductivity, whereas least value of conductivity is possessed by insulators. Semiconductors have in between the properties. Semiconductors have in between these properties. But one thing you will notice that in industries, though high conductivity is possessed by conductor, high resistivity is possessed by insulator, but maximum you use, see, you must have heard also of silicon, germanium, these are all semiconductors. These have excessive use, excess use. So excessive use of semiconductors is because of their ability to control current. That is one thing. We do not have transistors in our syllabus. Otherwise, this phenomena, how control current or how to control current, that was also included earlier. So now no need to go into the details because that's not a part of your syllabus. But just keep in mind that this ability is due to control the current. So excessive use of semiconductor is due to its ability to control current. Now, next classification involves band theory. That is very important. Band theory. Do one thing, note this page down, then we'll come to band theory. And any doubts you have in between from nuclei, atoms, any of the lessons, let me know. Also, class, I'm again asking you if you have those students who have not informed me, if you have got your schedules of pre-boards or if you know around which month your pre-boards are going to start from your school, so do let me know. Because see, this is the end. Last lesson we have started. I think 1 hour is left. We'll not be obviously able to finish this chapter, but a major portion we'll be able to cover. And whatever things will be left, we'll do it on Tuesday. Next week, you will have the gap. Then we have to start with the revision classes also. So I'll plan the revision classes accordingly, no? According to your pre-boards. So at least you are prepared for your pre-boards. Then boards will come. So all the students who know when their pre-boards are starting, exact precise schedule you have, then do let me know. For students who have a rough idea in whichever they month, they also let me know. And rest of you, please inquire about pre-boards, because that becomes the last opportunity to practice for the board exam properly in that environment. See, in this band theory, you have two energy bands. This is just a theory. You will understand how it is. There are two bands. One is a conduction band and another one is a valence band. Fine. This is known as band theory. So bands are basically energy levels. Everything we have studied it in atoms. We are talking about the same energy level only. When an electron jumps from one level to another level, it's just that one type of band, those are similar, we call them as valence band, and one type we call it as conduction band. Otherwise, it is a closely spaced energy level zone. Now, how conduction band and valence band differ each other? If you all have written the above part, differences between conductivity, resistivity, that above part. Written?
Yes, ma'am.
Yes, ma'am.
Only Atif and Krishna are there to respond in the class. Fatima also does. Others also keep on responding. At least it looks like you all are connected. Otherwise, I always have to call out names. Fine. See here. Valence band are those types of energy levels. These have electrons with them. But all these electrons are bonded electrons. These are bounded electrons you have over here. Fine. When some energy is, whichever is the energy required, that is present, then these electrons move into the region of conduction band. This electron then moves into the conduction band, and this then becomes the free electron which is available for conduction to occur. And this gap that you see over here, this gap is known as energy gap. Now, depending upon how much types of electrons are filled in conduction band, how much types of electrons are filled in valence band, what is the amount of energy gap present, what is the level of energy, how many energy states are present, what is the temperature. On the basis of all these things, you classify conductors, insulators, and semiconductors. So these are like energy levels. Some energy levels, these are all like energy levels. Like this, you have these energy levels. And you call this particular group as valence band. Same thing, this is also energy level. And you call this particular group as conduction band. So this particular one, this for the conduction band. This is the lowest energy level of conduction band. Lowest energy level of conduction band, lowest energy level. Because you can see for the conduction band, the one that is in contact with it, this is actually a very low level. Then it is increasing. But the conduction band that is closer here, this one, this is the highest energy level of valence band. Highest energy level of valence band. So let's see how the difference arises. Then only you'll be able to understand. Let's talk about conductors first. See, in case of conductors. In conductors, the conduction band is partly filled. Like this, the conduction band is partly filled with electrons. And then you have the valence band, which is fully filled with electrons. And there will be existing a certain energy gap. Or one more thing can happen. This is your conduction band. which has partly filled electrons, it can overlap with the valence band. This becomes the valence band, which is fully filled. This is overlapped. Fine. This is overlapped. So conduction band, this was the conduction band. See, understand one thing over here for conductors. Conduction band is partly filled, first point. Valence band is completely filled. Conduction band is partly filled is actually one difference point that you will see that is not present in rest of the two. Conduction band and valence band can overlap also with each other. They can either be present at certain distance or they can also overlap with each other. Some electrons can get overlapped. So whenever a certain amount of energy is striked up on the valence band, these are filled with electrons. These are completely filled with electrons. See here. This is showing, this is representing that these are completely filled and these are partly filled. Fine. So I think I've written also, yes, conduction band is partly filled, valence band is fully filled. Now coming to insulators, let us see that now the difference, then only you'll be able to figure and remember it. In case of insulators, what is the difference that arises? Conduction band is totally empty. Initially in conduction band, there is not a presence of a single electron. Conduction band is fully empty. And then you have valence band. Valence band is as usual, it is filled with electrons. This is filled with electrons. Here you have energy gap. This gap between the difference between the conduction band and valence band, this is known as energy gap. Now class, for insulators, remember this value. For insulators, energy gap should be greater than 3 electron volt only for conduction to occur in an insulator. So energy gap should be greater than 3 electron volt. So an electron from here, it will move on to the conduction band for conduction to occur. Understood? This is what is the case of insulators. Energy gap should be more than 3 electron volt. For example, if you take the case of diamond's energy gap is 6 electron volt. So by just looking at the number, even if you do not know diamond is a conductor, insulator, semiconductor, what it is, by just looking at 6 electron volt, you can figure it out that it is an insulator because that is definitely greater than 3 electron volts. So conduction band is empty, valence band is filled with electrons, energy band gap is large and greater than 3 electron volt. For example, case of diamond, that is 6 electron volt. So now from conductors and insulators, you can differentiate. Conductors mein kya tha? In case of conductors, you had the conduction band completely filled. Firstly, energy gap was low energy gap was there, but moreover, they can also overlap with each other. They could overlap with each other and conduction band was fully filled, partly filled. Yes, Akifa, you may read. Yes, Fatima, correct, good. That was partly filled and they can overlap with each other. In case of insulators, difference arises that conduction band is totally empty. First difference comes from here only. And second necessary condition for any element to become an insulator is to have the energy gap greater than 3 electrons. Now the last difference, that is for semiconductors. See, for semiconductors, just a slight difference that will arise. See, the conduction band is here also empty. Yahan pe bhi empty hai. Here also there is not a presence of a single electron in here. This is the valence band completely filled. Difference is between this energy gap. this energy gap is very low. This energy gap is less than 3 electron volt. For example, silicon, germanium, all these elements, like you have to remember the values of two elements, silicon and germanium. Other semiconductors are also present in your chemistry, so that you can have a look. But for physics, silicon and germanium are prime important, two elements. So silicon's value is 1.1 electron volt, which you have to remember. Germanium's value is 0.72 electron volt, which you have to remember. These two values you have to remember. So by looking at silicon's energy gap only, you can identify as it is 1.1, so it is less than 3 electron volt. It will be a semiconductor. Had it been greater, it would have been an inductor, right? So difference in semiconductor and insulator is between this energy gap only. Less than 3 electron volt, in insulator is more than 3 electron volts. And in conductors, conduction band is also partly filled. Clear? Band gap, band theory is clear. This was the band theory. Okay, good. Good. Note it down. Any doubts you have in between, let me know. This is a very theoretical part. Questions from this theory part will come to you. see classification of semiconductors, mainly the semiconductors are primarily classified into two groups. First group is known as the intrinsic semiconductors and the second group is known as the extrinsic semiconductors. Intrinsic semiconductors are mainly pure semiconductors. Pure semiconductors as in there are no addition of any element, no atom has been added, which we call doping. I'll tell you that when we'll reach extrinsic semiconductor. But in case of extrinsic semiconductors, they are impure. It means one single atom is present throughout. Now, depending upon the type of impurity that has been added, you have one type known as P-type semiconductors and you have other known as N-type semiconductors. You must have heard of P-type, N-type semiconductors. Before this, no, one basic thing just understand, because this hole and electron, this term we'll be using a lot. For example, let me tell you, make this as a note point and write it. Let's say this is one silicon atom, this is one silicon atom, silicon atom, silicon atom, silicon atom. There are the electrons of the silicon. Right? Now, and these are actually electrons are sharing each other, which is resulting in the formation of this covalent bond, right? And all these other silicon atoms are also present. Here also one silicon atom will be present, which will be joining us, like the silicon atoms are present. It basically results in the breaking of the electrons, breaking of all these electrons. So the negative particle that are present, these negative particles, which we call electrons, we treat them as negative. Electrons are treated as negative particle. But if I remove this electron from here, now a positive vacancy will be created. So positive vacancy that is known as holes. Positive vacancy, this is known as holes. So the negative electrons, these are known as the negative. We'll be treating the way we take electrons, protons. Holes are nothing. Holes are just deficiency of electrons, lack of electrons. But we take it separately. We write it separately as treating them as charged entities. Let me tell you, let's start with intrinsic semiconductors. Then you'll understand what is meant by this hole and what is meant by this electron when I say positive and negative. So these are pure semiconductors. These are pure semiconductors, intrinsic semiconductors. Here what will happen? This I have shown you. See, you can see here also all the atoms are silicon atoms only. All these atoms are just silicon atoms that are attached. These are electrons, electron of one. Instead of this, these are two electrons. This is the representation I have shown because this was given in your book. So that's why even you can draw these simple two electrons sharing like this, or you can take the two electrons, make it in this form. Fine. Now, from here, the electron moves, it becomes free and conducts electricity. What is meant by this? See, and one more in the class, when electron will leave, what will be created? Vacancy, deficiency of electrons, holes, exactly. And then it will lead to formation of holes. So if one electron will leave, one electron will be formed, right? If say two electrons leave, two holes will be formed. Three electrons leave, three holes will be formed. It means number of holes that are leaving are equal to number of holes forming. So number of electron is equal to number of holes. And actually what is happening? You are increasing the temperature. You increase the temperature. Means you increase the thermal energy. Somewhere you increase the thermal energy. So you increase the thermal temperature, you give them high amount of thermal energy. And because of this increase in temperature, the electrons break. Electrons may break because of this increment in the temperature. See, all these are linked through covalent bonds. All these are linked through covalent bonds. So this results into free electron because this electron bond, this gets broken. So this electron becomes free, available for conduction to occur. And ultimately, this free electron is only responsible for electricity, which you say conduction. So number of total atoms in intrinsic element is equal to number of electrons, which is equal to number of holes. Number of electrons and holes are directly equal to each other. Clear? Number of electrons is equal to number of holes. Now, if you want to draw the energy band gap also using the band theory, see how will it look like. This is the conduction band, let's say. This is the valence. So valence band is having number of electrons, some number of electrons which are present in the valence band. Fine. So here what will happen? The free electrons that will get free, these will move into the conduction band. These are what? These are free electrons. And whereas here what will be created in terms of these holes, positive holes will be created here. Positive vacancy, that are holes will be created. Holes will be created. So when you increase the temperature, when sufficient energy gap is met, and again these two values I have told you, you please remember it for silicon and germanium. And yes, what are the limitations of intrinsic semiconductors? Number of electrons and number of holes are very small. That is in the order of 10 to the power 6 per in 1 millimeter cube. You can say number of holes that are 10 to the power 6 holes are present. So it is very small. And energy gap that you observe, this energy gap is quite large. So energy gap is quite large. This is what is the mechanism behind intrinsic, because this is pure, so nothing is different. Not anything as such new you haven't come across, no. For extrinsic, you will see some elements should get added, should get deleted. But here for the time being, you cannot see any addition or deletion of any element. So rest of the things are same. Electrons leave, holes are created. Holes and electrons are treated as separate entities. Like holes are moving, electrons are moving. Like these terms will be used. Note it down. If you all have completed, I'll stop here on the next class. When your next class? Tuesday. So on Tuesday, we'll complete this lesson. And regarding the revision classes and everything, that I'll inform you on Tuesday only. So PN junction is a portion, but portion that is left from your syllabus. So that we'll complete on Tuesday. Tuesday will be the last class. After that, we'll have our revision classes. So all those who have completed, you all can leave. We'll continue this on Tuesday.